Hello guys, nice to see you. How are you doing?
Not bad. And you?
Good, thanks. So, last time we discussed different systems in terms of calculating capacitance. So we calculated capacitance of an isolated spherical conductor. Okay, good afternoon, everyone. Nice to see you. Also, we derived equations for the capacitance of parallel plate capacitor and cylindrical capacitor. So today we will consider one more example with spherical capacitance, and specifically we'll highlight some feature when the second larger spherical electrode will become very large. So we will see a transition from equation for the spherical capacitor to capacitance of an isolated central spherical electrode. So it will be the same as we derived initially for just isolated conductor. And then we will proceed further with discussing how to calculate equivalent capacitance of like batteries of capacitors which are connected in series or in parallel. So any combination of capacitors is possible to represent by just a single capacitor with some equivalent capacitance. So our goal will be to understand how to calculate this equivalent capacitance and why exactly it behaves this way and not another. Okay, so that's our plan for today. We'll see based on our time. Maybe we will also discuss energy of like accumulated in capacitors, but we'll see how it is going. Okay, then I will switch to our slides. Oh, it's not connected yet. So as I said, one more example of calculating capacitance when we deal with a spherical capacitor. Means we have two spheres. One is smaller with radius A and another bigger with radius B. So we have some positive charge Q accumulated on the surface of the first sphere and negative charge Q accumulated on the surface of the second larger sphere. So we know that electric field magnitude next to the charged sphere at some distance r is given by the following equation. E is equal to Ke, this electric constant, electric charge accumulated on the sphere, and divided by square distance from the center of the square to the point where this electric field is calculated. So now we want to determine potential difference between these two spheres. We can write it as VB minus VA, and that will be equal to minus integral from A to B, ER dr is like radial electric field. We just take advantage of the symmetry of this case, like spherical symmetry. And when we substitute for this electric field, this equation, we get the following. So it will be minus KEQ. These guys are constants, don't depend on position, from A to B, dr over r squared. So this integral will give us minus KEQ from 1 over r, and that is in the range from A to B. So eventually we get KEQ 1 over B minus 1 over A, and it will be KEQ A minus B divided by A times B. So that is the expression for the potential difference between points of the first and second spherical electrodes. So now we need to recall the expression, general expression for capacitance, and that is actually C equals to total charge divided by potential difference between electrodes. And if we now substitute for delta V this equation, KEQ A minus B divided by A times B, that will be equal Q we cancel. Eventually we will get A times B divided by KE B minus A. So that is the expression for capacitance of a spherical capacitor. Again, it is only about geometry. So we deal only with the radius of the central and external electrodes. Nothing else defines capacitance besides these two guys, like two parameters. And that is in the line with our previous findings for all capacitor systems, regardless of their geometry, like shape. All of them were like capacitance of all of their capacitance was determined only by the geometric factor. So now let us take a look a bit closer to this equation, and maybe first I will write it on the next slide. AB capacitance of the spherical capacitor will be K E. It's in the denominator. AB divided by K E B minus A. So if we consider some case when the radius of the external electrode, the larger one, approaches infinity, so B approaches infinity, then we can write that limit of B approaches infinity for this expression, A times B divided by KE B minus A. Then we can neglect with A in comparison to B, because B is approaching to very large value. So then we will get A times B Ke times B, cancel out B, and eventually get A divided by Ke, considering the value for this expression for the electric constant Ke, we can write that eventually we get 4 pi epsilon naught permittivity of free space times A. And this is the same equation which we derived previously for an isolated conductor. So capacitance of a spherical capacitor, assuming that the radius of the external spherical electrode is increasing to very large value, will approach capacitance of an isolated capacitor, isolated conductor defined by the central spherical electrode with radius A. So now we have such relationship with the final equation we derived for spherical capacitance of the spherical capacitor, with actually the first equation we derived on this sequence when we considered just an isolated spherical conductor. So now with this we can, already knowing how to calculate capacitance in different specific cases, can proceed further and deal with the connection of different capacitors in batteries and calculating so-called equivalent capacitance of capacitor batteries. So first, let us consider parallel connection of capacitors. Let's go to a new slide. How do we realize it? So we have two capacitors which are connected in parallel to each other and then connected to some battery. Plus, minus, we will have some positive charges accumulated on the right plates of those capacitors and negative charges on the left plates. There is some potential difference, delta V, between terminals of this battery. Then there will be also some potential difference between plates of these capacitors. So let's call this delta V1. Here will be delta V2. And also we have some charge accumulated at the first capacitor Q1 and charge accumulated at the second capacitor Q2. So probably you already know that a battery of capacitors can be represented by some equivalent capacitor. We have the same battery here, plus minus. So here is capacitance 1, here is capacitance 2. And here we have capacitance equivalent. So these electric circuits are the same in terms of total capacitance. And we can represent left circuit with the right one if we use the correct value of this equivalent capacitor. So now the question is how we calculate it. Going a little bit further, for parallel capacitance, parallel connection of capacitors, we can easily add capacitance of each capacitor and get equivalent capacitance. So C equivalent is equal to C1 plus C2. I'm sure you, like many of you, already know this. And the question here will be, how do we come to this conclusion? We need to prove that this is the case. So any ideas how we can approach this task in order to derive this simple equation, to find this simple relationship between equivalent capacitance and capacitances of each of capacitors in the battery when we have a parallel connection? So what will be the total charge accumulated by capacitors in this battery? Q total will be equal to Q1 plus Q2. Now, obviously, that if we have some equivalent capacitor, this equivalent capacitor should accumulate this total charge in order to represent the battery on the left side of this image. So if it accumulates this total charge, then Q total can be represented by C equivalent capacitance times delta V difference, potential difference, because here we have the same potential difference. They are the same because we use the same battery. So we can write that C equivalent times potential difference is equal to Q1 plus Q2. How do we express electric charge accumulated by a capacitor in other terms, so related to capacitance and potential difference? For each capacitor, we have its capacitance and potential difference between electrodes. So the product of capacitance and potential difference gives us the electric charge accumulated by this capacitor. So following this principle, we can write here C1 times delta V1 plus C2 times delta V2. So now we have kind of a relationship between equivalent capacitance and capacitance of each of these capacitors connected in parallel. However, we have still potential difference delta V, delta V1, and delta V2. What is nice about parallel capacitance, parallel connection of capacitors? The potential difference between plates of each capacitor and the terminals of the battery, they will be the same. Means that delta V is equal to delta V1 and is equal to delta V2. 2. So we can actually substitute delta V1 and delta V2 with delta V. So let us do it here. We can delete this V1 and V2. We have delta V. And in this case, we can easily cancel it out. So take it out from parentheses. From left and right side, we have delta V, so we get rid of it. We can eventually, we have our equation. C equivalent is equal to C1 plus C2. So that is this relationship between equivalent capacitance of two capacitors connected in series, in parallel. And if we have more, then we just continue this. So it will be plus Cn. So that is the way how we derive this relationship, and indeed show that the sum of capacitance of parallel capacitors will give us equivalent capacitance of the battery. If you remember this, it will be really easy to catch up later, even if you forget some specific rules how capacitors should be, equivalent capacitors should be calculated. So now we are done with parallel capacitors connection, and we can proceed with the series connection of capacitors. So let us consider some battery of capacitors which are connected in series. We have capacitor 1 and capacitor 2. Here is battery with some potential difference between terminals delta V minus plus. And then let's see what's going on at our capacitors. At the left electrode of the first capacitor, let's call it C1, C2, we will have accumulation of negative charge. At the right plate of the second capacitor will be some positive charge. Now, obviously, for other plates of the first and second capacitors, we get positive and negative charges. Also, we can maybe highlight here that we have Q1 negative at this plate, then this plate will give us Q1 positive. Why it's positive? Then we have for this plate Q2 negative, and for the last plate Q2 positive. So now we also need to highlight that there are some potential differences. Delta V1 and delta V2 for each of our capacitors between their plates. So with this information, we need to think how we derive this equation which will relate capacitors C1 and C2 with some equivalent capacitor, which can substitute this battery. So it's C equivalent here plus, no, it's different. Minus plus, the same potential difference. And here will be Q also, total charge accumulated by this equivalent capacitor. So how we find the relationship between C equivalent and C1, C2, or Cn, depends how many capacitors we connect in series. So in this case, we cannot write that delta V is equal to delta V1 is equal to delta V2. So that is not true because we don't have parallel connection. So we have series connection, and in contrary to that, we actually need to write the delta V, potential difference between terminals of the battery, is equal. Any suggestions what it will be equal to? Taking into account series connection of this.
1 divided by V1 plus 1 divided by V2.
No, that is,
No, it's just V1 plus V2.
yes, exactly. You are right. V1, delta V1 plus delta V2. So 1 over, we will come to that point, but that will be a bit different story. So we have first delta V1, then we add to this delta V2, and the sum of these two guys should give us the total potential difference, which is provided to this circuit of two capacitors connected in series from terminals of this battery. Okay. So with this in mind, we proceed further. We will come back to this point a bit later. So now what is interesting is to look a little bit closer to the charges which are accumulated on these plates. So let me draw it separately so we don't make it too crowded. So we have two capacitors connected in series. Here we have minus, here we have plus, here minus, and here plus. Now, if you take a look at these plates, means we have right plate of the left capacitor or first capacitor and left plate of the right capacitor or second capacitor. They are connected with a conductor between each other. Means that these plates together with the conductor, like some wire, they form just a single conductor isolated from everything else, because in between plates in the capacitor we just have vacuum. There is no connection between this red part of the red conductor with the external world in terms of electrical connection. So if we have such a case, then initially, when we didn't, like before we connected this battery to this capacitors, everything was neutral. We didn't have any charges. Then we connected this battery. We accumulated some negative charge here, some positive charge here. And obviously, we, oh, sorry, that is wrong polarity here. It should be plus and minus. So obviously, there should be this opposite by sign, but equal by magnitude charges accumulated at the opposite plates of the first and second capacitor. If initially this conductor marked as in red was neutral, it didn't have any connection to external circuits, so we could not provide or extract any charges from this internal isolated conductor. Means that these charges, positive and negative on the plates from left and right, they are because of polarization and the redistribution of charges inside this conductor. So if it was neutral before, it remains isolated, means we could not provide or take away any charges. It should be neutral after also, because it was isolated from the circuit. If it remains neutral after connecting this battery to the capacitors, means that charge Q plus and charge Q minus, they are equal by magnitude. So absolute value of Q plus should be equal to absolute value of Q minus. That means that charges accumulated by each of these capacitors will be equal in the case of their series connection. So we can write that Q one is equal to Q2, and instead we can use just some charge Q. So that comes from the principle of electrical neutrality of this internal isolated conductor, which consists of plate from the first right plate of the first capacitor, left plate of the second capacitor, and metal wire which connects them. And they are isolated. They were electrically neutral before. They are electrically neutral, like this conductor is electrically neutral after connecting the battery. Based on these ideas of electrical neutrality, we can state that these charges accumulated by two capacitors, regardless of their capacitance, they can be different, but the charges which are accumulated by these capacitors, they will be the same. So that is written here. And now we need to define electric charge, potential difference, delta V1 and delta V2 between the plates of first and second capacitors in terms of electric charge accumulated by this capacitor and its capacitance. So we know that potential difference delta V1 should be equal to electric charge accumulated by capacitor divided by its capacitance, which is C1. The same we can write for potential difference between the plates of the second capacitor. That is Q divided by C2. Also, following the same concept, we can write that delta V total potential difference is equal to this charge Q divided by C equivalent. Now we come back to our previously written equation, which relates potential difference of at the terminal of the battery and potential differences over each capacitors. Substitute there these equations and get the following. So we have Q divided by C equivalent is equal, so that stands for delta V. Instead of delta V1, we substitute Q divided by C1 plus Q divided by C2. So now we can get rid of this Q because it's the same. So eventually 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So that is the equation which gives us the relationship between equivalent capacitance of 2 or more. We can continue here, 1 over Cn, capacitors connected in series. And as opposite to parallel connection, when we have the sum of all capacitance, and that will be equal to equivalent capacitance. Equivalent capacitance of capacitors connected in series will be smaller than the smallest capacitance of included in this series connection. So that you should remember, because later we will have relationship between equivalent resistance of resistors connected in series and in parallel. And that will be in the contrary to the final equations of equivalent capacitors. So please remember this so you don't mess it up in the future. You need to know that for capacitors, in the series connection of capacitors, we get smaller capacitance of the smallest capacitor connected in series. And for the parallel connection of capacitors, we just get the sum of all capacitors connected to this battery. So this is the information and explanation why we get these final equations for calculation of equivalent capacitance. And that's quite important because you will deal with this solving many problems. It will be necessary to calculate equivalent capacitance of different cases. And further, we will proceed with calculation of electric energy accumulated in a capacitor, which is charged to some potential difference, some given potential difference. So I believe that by the time we will not manage that topic today, so we probably will leave it for tomorrow, for next discussion, which will be on Friday. I think that the main message to take home is to clearly understand why and how we calculate equivalent capacitance for series and parallel connection of capacitors. Keep that in mind and make it clear for yourself for future, because it should be kind of well known and you will use it quite often. So if you have any questions regarding this topic, you're welcome. So I believe everything was clear. Then thank you for attention. Have a good day and see you on Friday.
Thank you.
Bye bye.
Thank you. Goodbye.
Take
Thank you,
care.
goodbye.
Thank you, goodbye.
Bye bye.